everyone. So in the next set of videos, we're going to be continuing to explore and refine our skills in natural deduction. So chapter 8 of the Baronet textbook introduced us to the idea of natural deduction by giving us the first four implication rules. And these are rules that are really building off of some things we've already come to know about truth function in the chapter on propositional logic and the building of truth tables. Some of these rules are sort of implicit in those truth functional rules for the logical operators. Some of them introduce some new information. But in any event, in this video, I want to review a little bit the first four implication rules in order to kind of help you start to have a feel for them, and then to introduce you to the second set of implication rules, and then show you a little bit how we go about the business in natural deduction of setting up a proof which builds off of a set of premises and is given a conclusion, but for which there is missing information or missing steps in the argument. So remember, our first rule is modus ponens, or MP. Modus ponens works with the conditional statement if P then Q, where in the second premise we have the antecedent P affirmed. If the antecedent P is affirmed, we can immediately infer in the conclusion Q. We can affirm the consequent Q. Now watch out for the fallacy of affirming the consequent. It does not work the other way. So if we were to see Q affirmed in the second premise of the argument, we couldn't affirm P. That is not how modus ponens works. So modus ponens is a very high frequency rule that we will employ regularly throughout the chapter. So I really urge you to kind of have it under your belt. Try to write it down a lot, and it's very useful to be able to know it when you see it, and to be able to play with it and to plug it in with great ease. Modus tollens is our second rule, and modus tollens is in a way very close to modus ponens, not only in its name, but also for the fact that it works with a conditional, if P then Q. We're starting with a conditional again, except that in the next premise, rather than affirming the antecedent, we deny the consequent. We have a not Q, right? And so what modus tollens allows us to do is infer the denial of the consequent, not P. All right, so modus tollens holds if P then Q, not Q, therefore not P. Now again, there's a kind of a false friend here, which would be the denial of the antecedent. Modus tollens does not allow you to infer the denial of the consequent from the denial of the antecedent. So if we had a negative, if we had not P in the second line, we couldn't affirm not Q in the conclusion. It only works through the denial of the consequent. Okay. Moving on to hypothetical syllogism. The hypothetical syllogism, or HS, works with two conditionals that take the form if P then Q, if Q then R, therefore if P then R. And I kind of urge you to pick up the pattern that occurs here in order to kind of have some feel for the logic of the inference that's being made. Hypothetical syllogism is basically working with the repetition of the consequent Q in the antecedent position in the second premise. And then we have a repetition of the consequent in the last premise as the consequent of the conclusion. And then you will see that the antecedent P is repeated as the antecedent P in the conclusion. I apologize, that looks a little messy, but you can see that this pattern is taking a kind of a definite shape here. All right. The other thing to bear in mind with hypothetical syllogism is that the order of premises 1 and 2 can be flip-flopped. They can be reversed. We can have if Q then R appearing before if P then Q and still make the inference to if P then R. So the order of premises 1 and 2 is of no consequence. Okay. The disjunctive syllogism is a nice rule that allows us to, in a way, disassemble any disjunction from the truth functional status of disjunctions. Remember, disjunctions are really either or statements. And so if we are affirming in a premise that a disjunction, a wedge, is true, it means that at least one of the disjuncts is true. So in the second premise, we see that one of the disjuncts is denied, not P. So that we can affirm, or we can infer logically that Q must be the disjunct that is true, because otherwise either P or Q wouldn't be true at all. We would have two false disjuncts, and therefore the disjunction as a whole would be false. So the disjunction is a very nice, clean way of disassembling disjunctions through the denial of one of the disjuncts, provided that that is given to us in one of our premises, that allows us to, in a way, pluck apart the disjunction and drag down in the next line our second disjunct. The disjunctive syllogism works either way. Either of the disjuncts can be negated, with the result that we can infer the truthfulness of the other, P. So with this one, either P or Q, we have not Q in the second premise, therefore P is true. All right? So think about natural deduction as a logic of assembly and disassembly. These are kind of like little Lego pieces, as it were, that we are ripping apart and building back together again in order to get new lines to fill in the missing steps of a longer proof. All right. So that's the first set of rules of implication. You should try to, at least in the near future, have them very much under your belt, be able to write them down, be able to recite them. The closer you have these to in your memory, the more easy they are to work with. Now let's talk about the second set of implication rules. Implication rules 2 will also be drawing on a lot of what we already know about truth functional values from the truth tables, with a couple of provisos and additional bits of information here. But our first rule within the second set is known as simplification, or simp for short. So simplification is simply working with a conjunction, and what we know about conjunction is that if a dot is conjoining two conjuncts and we are affirming that the conjunction is true, we know that both of those conjuncts taken together have to be true too. You cannot have a false conjunct and have a true conjunction as a whole. So for any conjunction P and Q, we can infer that P has to be true, right? If P were false, P and Q would not be true. So it cuts the other way too. For the same conjunction P and Q, we can infer the other conjunction, the other conjunct Q must be true as well. So conjunction simplification is a very nice way of disassembling a conjunction where perhaps we have a complex statement that is working with a conjunction. Very often we might want to isolate one of those variables, and we can isolate it by applying simp, or simplification, because of the truth functional status of conjunction. Okay, so the next rule in the second set of implication rules is known as conjunction, or just simply conj. And conj is kind of the flip side of conjunction, is the flip side of simplification. Whereas simplification was ripping apart, conjunction is conjoining, it is building together. So for any premises P, Q, we can conjoin them in an inferential way, right? Because if this premise is saying that P is true, and this premise is saying that Q is true, well, we can infer that their conjunction is true too. Dot has to be true because both of the conjuncts is true. So conjunction can be a nice way of moving from simple single variables to a more complex statement that are conjoined or brought together at the hip through the truth function of the dot. Okay, addition or add is a very useful rule, although some people find it to be a little bit annoying, and it's sort of easy to forget because addition is not necessarily working with information that has already been given to us in the premises of the argument, but what it really is drawing from is the logic of the disjunction. And the disjunction is an either-or statement in which only one of the disjuncts had to be true for the disjunction as a whole to be true. So this is kind of a nifty trick, because if we have a variable P, which is being affirmed as true, we can add anything we like to it in the world, essentially, in the conclusion, and have a true claim. Either P or Q is also true, We know that by necessity because P is true, and as long as you have one true disjunct, you know that the disjunction as a whole is true. So Q could be true or it could be false. It doesn't matter. It doesn't affect the truth status of either P or Q because we already know from the premise that P is true. So this means that we could actually add to P anything we like. We could add a long, meandering, complex sentence with parentheses and brackets and multiple parts, and we don't have to know anything about whether or not that sentence is true or false. As long as it is added with the wedge to P, we know that the sentence is still true as a whole. So that can be a very useful way of building up a complex statement from something that is simpler if we need to get there to derive the conclusion. Okay. Constructive dilemma is the last rule in our set, or CD, and constructive dilemma is a little bit tricky. As you can see, it's a little bit convoluted, but really it's just bringing together through conjunction two different conditionals. We have a conditional as the first conjunct and a conditional as the second conjunct. So the first premise reads both if P then Q and if R then S. And then the second premise is really a disjunction of the antecedents, P or R. So we have P or R brought together in the second premise. And then what we can infer in the conclusion is the disjunction of the consequence, either R or S. So this is a very useful rule when you are seeing a lot of conditionals and a conjunction, and you think you might have to generate a new disjunction. Constructive dilemma might be the rule that you need to apply. This one will take a little bit of time to certainly learn and to memorize and be able to identify, but think a bit about it as the conjunction of two conditionals where lines are generated such that we're able to get to the disjunction of the consequence. Okay? So once we have these, we have our first complete set of implication rules, sets 1 and 2, with a total of 8. Now let's look at an ordinary language example of an argument that comes out of some theology, some medieval philosophy. Sometimes it can be a little bit confusing to do natural deduction when we're only looking at the formal propositional logic, not any content. So what I've tried to do here is given you an incomplete argument from medieval philosophy that we will then try to formalize and see if the argument is valid or not. So let's have this premise be our Kickstarter. Number 1 says evil exists. Premise 2 says if evil exists, God cannot be all powerful. Premise 3 says if evil exists, God cannot be all good. So, therefore, God is not all powerful and he is not all good. Okay, a lot going on here. We have to kind of examine what our operators are, or really what our connectives are, and see if we can't translate them into symbolic notation. So I'm going to translate the first premise into the single proposition E. E standing in for evil exists. Evil exists has no connective, so we don't need a logical operator. This is just a simple proposition without a connective. Proposition 2, it seems to me, is a conditional. If evil exists, God is not all-powerful. So to be all-powerful, I'm going to symbolize with P, and we have the negation of P as the consequent. So premise 2 reads, if E, then not P. In line 3, we have another conditional, right? If E, then not G, where G stands for being all good. And so in this case, the consequent would be not G. If evil exists, then God is not all good. And then we have as our conclusion, and we are always going to notate the conclusion over to the right here with the forward slash. This is our conclusion, and this is how it will always be formatted in natural deduction moving forward, with the last conclusion appearing next to the last premise, set off to the right with a forward dash. And our conclusion says both not P and not G. So if God is not all powerful, he is not all good. All right, so this is a formalization of this, maybe not ordinary language example, but argument with content. And let's see if we can't derive the lines that are missing in this argument. You'll notice that we haven't quite gotten from the premises to the conclusion, although they might be buried in that conclusion. So let's see if using the rules of implication, we can supply the missing steps in the argument. All right, so how do we derive the conclusion? When we have our premises and our conclusion, what we are trying to do essentially is use the rules of implication to get over to this conclusion, both not P and not G. So we are kind of working with premises 1 through 3 as our stepping stones from which we are going to generate new lines that hopefully can take us to the conclusion, both not P and not G. So in line 4, what we're going to do is generate a new statement using one of the rules of implication. So if I've given you not P as the new line in line 4, and I'm telling you that we are going to use lines 1 and 2 to generate line 4, try to think about what rule it is that justifies that move. How do we get in line 4 not P by using lines 1 and 2? Which rule of implication does it to take not P as a single variable? Okay, take a look, if you're stumped, at line 2, and you'll notice that line 2 is a conditional. Very often with a conditional, we're going to be using modus ponens, right? Modus ponens is a very high frequency rule that allows us to make an inference when we have an antecedent that is affirmed. So modus ponens says, if P then Q, P, therefore Q. Antecedent is affirmed, we can infer the consequent Q. Well, in line 2, I have this conditional if E then not P. And in line 1, I do have my antecedent affirmed. I have a premise saying E is true. That's all that premise 1 is saying. So if E is true, I am able to infer the consequent, not P, in line 4. So this is a perfect application of modus ponens. So the rule that we have used is MP. So whenever we are citing our lines, in other words, whenever we're generating new lines to a proof, we cite the lines that we have used, 1 and 2, and then we cite the rule that justifies the step, modus ponens. All right? So we've used lines 1 and 2, so I'm going to cross them off. I think it is a very useful strategy to cross off lines that you have used, even though you can go back and use them again, because very often we're not going to have to recycle lines. We're very often going to have to look for new parts of the argument that haven't been used before to get to the conclusion. Okay? Now what's next? Now, line 5 is going to generate not G. So let's see how we can get not G taken by itself here. If I look back, I see that we have, again, on line 4, not P. So however are we going to get not G taken together? Can we do that? Look back on all of the premises, really, 1 through 4, and see if a rule can be applied to any of them that can get not G in isolation. All right, so how do we do this? Well, much as we used modus ponens last time, I think modus ponens works again for us in line 3. You will see that we have another conditional in line 3, if E, then not G. And we have this antecedent E affirmed in line 1 here. So I can do the same move, as I did in the previous line, just by applying modus ponens to lines 1 and 3 rather than line 1 and 2. So lines 1 and 2, lines 1 and 3 allows us to isolate not G, because when we have the antecedent E affirmed, we can infer not G. We can affirm the consequent, not G. So in this case, we would cite lines 1 and 3, and we would cite modus ponens as our rule again. Okay? Now let's look at line 6. We have finally both not P and not G. So how do we get there? Try to find a rule that can be applied to lines 1 through 5, any of those lines, that would bring together finally not P and not G. Okay. Looking back at lines 4, I see that we have not P taken in isolation. And looking at line 5, I see we have not G. So when we're thinking about a rule that will be very useful for us in bringing together two variables, I like the rule conjunction or conj as the way to go. Conj basically holds that for any variables P, Q, we can affirm their conjunction, both P and Q. And this is still true with negatives, both not P and not G. So for line 6, we would cite lines 4 and 5, and we would cite the rule conj as justification for the step. Okay, so we cross off line 4, line 5, and we've used line 3. And we see that both not P and not G is our conclusion. So we have concluded the argument. We have derived the conclusion from the premises. We needed 1, 2, 3 more lines to get there. And we needed 2 usages of modus ponens and 1 usage of conjunction to generate the conclusion. So to put the argument back into ordinary language, line 1 says evil exists. Line 2 says if evil exists, then God is not all powerful. Line 3 says if evil exists, then God is not all good. Line 4 says God is not all powerful. Line 5 says God is not all good. Line 6 says God is both not all powerful and not all good. And that was kind of the extra couple of hiccups we needed to get from our premises to our conclusion. All right, so this is kind of the derivation procedure for natural deduction. We are pulling out new lines by using our rules of implication, and then we are indicating what those rules were that justified the new steps to the argument. So setting up the proof is basically a kind of formal process that has sort of a formatting procedure. When given premises and a conclusion, your premises will always be numbered vertically to the left, like we just saw, and the conclusion will always be set off to the right with that forward dash, indicating that that's where the conclusion is appearing. Okay, so arguments always kind of take this format. We have premises, and then we have a conclusion. Lines 1 through 3 are the premises, and then our conclusion is set off by the forward dash S. All right. So let's have a little bit of work here, and see if we can generate new lines with our rules of implication to get to this conclusion S. All right. So what do we have here? We have a disjunction, we have a negation of just a simple variable, and then we have a conditional in line 3. So what's line 4 going to be? What are we going to generate? A good rule of thumb is to look at our conclusion and maybe try to get a little bit strategic, or at least have some sense of orientation of where we're headed. Well, our conclusion is an S. I see that S is appearing in line 3 as the consequent of that conditional. Can we work with line 3 to begin with? I don't really see a rule that allows us to work with line 3 first, so we have to backtrack a little bit. Now I do see in line 1 and 2 something that might be a leaping off point. I see a disjunction, either P or Q, and then I see that one of our disjuncts is negated in line 1 with not P. So I like the rule disjunctive syllogism as a way that we could go about generating a new line. Remember, disjunctive syllogism holds that for any disjunction, either P or Q, the negation of P allows us to infer the other disjunct, Q. So in line 4, I am going to isolate that disjunct, Q. We're using lines 1 and 2 to do it. So we have to have this kind of underline here to indicate that this is our citation. And I'm going to write line 1 and 2 and DS as the rule that justified that step. So we have Q in isolation here by taking together lines 1 and 2 and applying disjunctive syllogism to it. Okay, now let's move forward a little bit and see if there's anything further we can do to get to our conclusion S. Well, I see in line 3 a conditional, and I see in line 4 the affirmation of our antecedent. So recall our rule for modus ponens takes that form. If P then Q, where the antecedent is affirmed P, we can infer the consequent Q. So in line 5, I'm going to use modus ponens to isolate S. We have the affirmation of the antecedent Q such that we can isolate S. So I'm going to cite lines 3 and 4 and cite my rule modus ponens, MP, and then cross off 3 and 4. And once we are there, we have S. We have arrived at our conclusion. So this is a complete proof procedure, which required 2 lines and 2 rules, disjunctive syllogism and modus ponens. All right. Okay, I've kind of walked you through this, but this is just a cleaned up version of it, if you care to write it down again. Now, a couple things to bear in mind. Even though I was crossing off rules as I use them, you can recycle the premises as many times as you need to get to the conclusion. There's no limit on that, but just bear in mind that for smaller arguments, usually you will only need to use lines once. Usually once you have used a line, you will have to move forward and use new parts of the argument to get there. All right. Couple of derivation tips. As you're learning the rules, you should have a rule sheet next to you and look from the rules to exercise to start recognizing the structure. In other words, there's no harm in looking back at our rules of implication over and over and over again, writing them down, jot them down. There's no harm in repeating this until it becomes more familiar, until it becomes more of a habit for you. These rules are a little bit strange at first, and there's nothing all that intuitive about them until you just drill them over and over again. Try to work backwards from the conclusion. You should always be thinking about the conclusion as the goal of the derivation. So look at the conclusion and try to recognize whether or not it is appearing in the conclusion. Try to get some sense of directionality to where you are working, because otherwise you can get very easily frustrated and not even know where to begin the derivation. Try to pull lines out to the side and away from the business of the proof to help make clear what inference options you have. In other words, have some paper over where you're writing down your rules and you're writing down specific premises. It's okay to make mistakes and have to go back and retrace your steps a little bit. Some of this does just require some trial and error. Um, let's practice just a little bit identifying valid and invalid arguments on the basis of our rules of implication. If I have an argument like this, if A then B, A, therefore B, would you say this is valid or invalid based on what we now know about the rules of implication? This is valid, right? This is valid. This is equivalent to modus ponens, right? Where we have the affirmation of the antecedent. If P then Q, P, therefore Q. This is equivalent and a valid natural deduction. What about this argument? If A then B, B, therefore A. This one is invalid. Remember, this is the fallacy of affirming the consequent. Modus ponens does not allow us to infer the antecedent from the affirmation of the consequent. It's one of our false friends out there, so be wary of any premise that seems to isolate or affirm, rather, the consequent. You can't use modus ponens in this way. This argument, well, I've given away to you, but just have a look at it. If A then B, not A, therefore not B. This would be an invalid application of modus tollens, right? Modus tollens, remember, is any argument that takes the form of denying the consequent. If P, then Q, not Q, therefore not P. Modus tollens, however, does not go the other way. We can't infer the denial of the consequent from the denial of the antecedent. Okay? All right, so just to recap briefly, these are our first four rules of implication: modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, and then we have entered the terrain of the second set of implication rules: simplification or simp, which just refers to a simplification of a conjunction, P and Q. Conjunction or conj, which brings together standalone variables into a conjunction, P and Q. Addition allows us to add any statement we like to a simple statement, P, through disjunction, P or Q. And then constructive dilemma is the conjunction of two conditionals, both if P then Q and if R then S. Either P or R, therefore either Q or S. Okay, write these down several times before moving on to the next video. In the next video, we will reiterate and repeat some of this stuff and do some further practice on generating new lines that use citations and rules to justify the missing steps of a complete proof. Thank you, everyone.